Yeah, to put it short, my job is pretty similar to my previous speaker. I take your results and bring it to society. And what I would like to do here is I would like to take, let's say, an orthogonal perspective to AI. So in the last 1.5 days, we looked at AI pretty much as a tool set for, well, detecting specific signals or patterns within data sets. And I want to use now a different perspective that pretty much builds on what Manil showed us this morning. So the idea is really to ask questions. And if you want to ask your environment a specific question that the environment should answer, there are a number of prerequisites that we need to have fulfilled so that this can actually work. This is some research currently done within the OGC. So for those of you not very familiar, the OGC is mostly known as a standardization organization, which it is for the last 30 years. But the bigger part of OGC is actually what we call collaborative solutions and innovation. It's a large research program where we test how we can bring results from the academic research together with results from the private industry for the sake and for the impact in society. So if we look at spatial data and the discovery and integration of spatial data, this is a slide that is roughly 30 years old, right? The only things probably added are the tablets and the phones. But the publish, find, bind pattern is how research was done for, well, several decades now, right? On the top, you have the data providers or the service providers, the analytics providers. They register their data in some sort of a portal. This can be whatever, Copernicus servers, European Science Cloud. It can be data in NASA DAX or other platforms. It can be NVIDIA's new Earth 2 environment, right, that you can ask all sorts of questions. And then it is registered in this, let's say, first of all, catalog environment, and then the actual users discover the data and the analytical functions in this environment and ideally connect to them and use them. Even though the slide is about 30 years old, it's still reality in about 80%, well, yeah, probably 80% of the cases. You can easily match it to the more modern cloud environments, right? You do have still your data and service providers. They now register everything within a specific cloud environment. And then you have the user community at the lower right that still needs to discover the elements within the cloud environment and then will either download and do the processing manually or more and more actually run the execution in the cloud environment close to the physical location of the data. So what's now the challenge? The challenge, well, it's usually twofold, right? Two major challenges. If we think of large data sets like Sentinel imagery or others, you usually know where to find these data sets, right? This is a simple discovery task. But then you run into the situation we already discussed this morning, a situation about costs. You need to process it. And we are running these initiatives, these research initiatives in OGC, about 20 per year right now. And in every initiative, we have the same problem, and that is who pays for the cloud processing. And I know very few institutions that tell me that they don't have a problem with cloud costs. So almost every researcher does have a challenge. So what do we need to do? Well, we need to make intermediate products and results available. We need to think about clever caching mechanisms that allow others to reuse what was produced before, right? Because it's probably much cheaper to reuse than to run the same calculations over and over. But there's not only big data sets out there, right? In many real-world situations, you need to integrate local data sets that may not even come from remote sensing, but from in situ sensors. So if you want to, for example, calculate a heat map for Berlin, what's the ideal temperature data that you can obtain? Well, the ideal temperature data probably comes from cars, right? Every car has a temperature sensor these days. They drive around all day. So just take the data from these cars, but you can't connect to it, right? You don't find it. There's not even a product that is probably offering these data sets. Or maybe there is, and you haven't discovered it. So we have two aspects, right? One is reusability for those things that you have discovered, because if you can't reuse, then it gets expensive. And on the other side, we have the findability. So if you can't even find the data you need for your specific challenge, you cannot get engaged with the research you're interested in. So that's the situation, right? Assume you want to do a heat island simulation for Berlin, or you want to run a simulation model for Berlin, and you want to assume that you convert 20% of the parking spaces into green spaces. That's a classical real-world situation, right? It is not, like we discussed already this morning, right? Not this very, very specific scientific challenge. It is quite a series of challenges that you need to solve. And I mean, I would love to run this query against Manil's tool, right, to see if we actually get an answer out of it. And as long as you are within a single environment, you may have the chance to get it, right? Maybe there is a single heat island simulation model available. Maybe there is a single temperature data set available. And then you can do these calculations. But most likely it is not. Most likely you have either in your single environment already more than one possible data set that you can use, or you are dependent on data coming from quite a number of different environments. So what do we need to do? Well, we need to see that we need to discover all these different data sets that are served by these other environments. And if we go back to this old picture here, right, the issue why it is not really satisfying is that discovery never worked. There is no catalog for data. And I'm constantly told, yes, there are lots of catalogs for data. And if you try to find the data you need for this real, and one of the reasons is that you often don't know what to ask for, right? The problem with data is it follows no language, right? So if we go to a question like this, and we now use and think about large language models, well, the ones we use, like the ChatGPTs, right, built on this enormous corpus of data, well, this is all natural languages. And natural languages have a clear syntax, a clear grammar, they have very specific rules. You may add imagery and audio files, you may add computer languages, programming languages, for example, but they all follow similar patterns. So it's rather easy for the model to learn on these sources, right? You just go out, heat island, you query all these websites, and you learn quite a bit about it, and then you can probably understand what a heat island is, right? This works, right? What is a heat island? You get a good answer to such a question. You even understand if you, I mean, this is DAL-E, right? You can ask these engines to produce something, but here you see that the engine doesn't really get it fully right? It has something to do with the sun, okay, well, most likely. It has something to do with green structures and with the very much built-up environments, but, well, the peak of the temperature here is where it's greenest, right? This is probably not exactly right. So the tools understand parts of it, pieces of it, but they don't understand it fully. And that is a big challenge if we want to use AI tools for discovery, integration, and reusability. So the tool discovers it, right? The tool discovers all these sources about the urban heat islands, even handles all the acronyms and different languages. Well, that all works, but data is just random, right? You can express your data in an almost endless number of ways. So take a very simple Excel spreadsheet where you have 50 columns of data. You may have column headers, you may not. You may have cryptic column headers that only you understand. You may have very descriptive column headers that others understand. You may have column headers others think they understand, but they actually misunderstand because your definition was different, right? So data is, if you look at it from a, I want to learn what data you used and how I can automatically integrate it, it looks, well, like data gibberish, right? It's hard to integrate. So if you want to build something like a large language model for data or analytics, it needs help, right? We cannot just feed all our data repositories and then hope that the environment, the AI environment, will actually come up with helpful mechanisms, or well, with mechanisms that help us to solve our challenges. What do we need to do? Well, we need to help them, right? We need to make the large language models understand the data, understand the analytics, and understand the meaningful connections, right? Connections as such, okay, well, that might work, but meaningful connections are key. So this is the current situation. The current situation, you have all these silos, and yes, they may be connected at a very low level, right? They may be all connected to the internet. You can access them via different protocols. But pretty much it's a siloed environment. As long as you are within one silo, so we just heard about Google Earth Engine, you can do fantastic research and analysis, right? You can do produce data that really changes the decisions made all over the world. So that's fantastic. But in many situations, you need to bring at least 2 or 3 or any number of these silos together to answer your questions and your challenges. And how to do this, right? So if we look at this statement again, we want to run this simulation model. Well, first, we do have these different feature types, right? We have heat islands, parking spaces, green spaces. And the question is, well, if I produce some data set, for example, about green spaces, what's my definition of green spaces? What's the characteristics of the grassland versus the shrubs versus the trees, the forest, and so on? I need to understand it very precisely, because otherwise, if I have something misinterpreted, right, you have your little patch of grassland, well, after 8 weeks without rain, this patch of grassland doesn't have many green elements left, right, and pretty much behaves like a parking space that is pure concrete or asphalt. So these feature types should be described in feature type catalogs, which are at the most rudimentary level. These are just controlled vocabularies. We need to link every attribute and every value that we use to controlled vocabularies. And even though this is the most intuitive thing, right, whenever you see a data set, try to figure out what they mean with R_P equals 12. This is the most common pattern used in almost all data we find. It is not providing sufficient information what all these attributes actually mean, what are the dimensions for the data. But it's not hard, right? You could use just a URL for your attribute name, or you can use some mechanisms that provide you a namespace declaration, and then you know, okay, where to get the descriptions of the data. But this is almost never the case, almost never. And then the issue is, well, we don't have one of these control vocabularies, we have many of them. But how many people, when they publish their research, provide the links to the definitions of each element within the data? Who has ever published a paper that does this? Okay, well, that is a clear message. And then, I mean, what we want is, if we do find heat islands, right, described and defined in several of these repositories, we need to have clearly defined connections between these individual repositories, right? You don't want to copy, paste, and then modify, right? You want to make sure you say exactly, okay, I do use this as the base, but I profile it in a specific way. Or I use this description over here, but I have extended with the following mechanisms. And we need to do this in a machine-readable way. If we don't do it in a machine-readable way, it's completely useless, because it means only humans can understand it. They may not in most cases, but they at least know that they don't understand it and may figure out some ways to learn what you actually meant with your attribute. But this is still the classical thing, right? We love to reinvent. We invent our own things over and over because, for sure, our research is special, right? It's just the most natural human behavior is reinventing the wheel. And if you don't want to reinvent because we are lazy, and I mean, most of us are lazy, we copy, paste, and then we modify. Well, this is perfectly fine as long as we use, again, a machine-readable mechanism that expresses clearly where we copy it from. The only issue is that you lose the connection to the original source. So imagine there is some data out there that you used within your analytics, and then you produce some results that might be interesting to others. If you have copy-pasted the data, well, you lost the connection to the original source, and every change applied to this original source will have zero influence and impact on your results, right? Because you just don't learn that it has been changed. And then the modification aspect is a big challenge because you think someone uses someone from someone else. But it's not the case because it got modified just in a way that you don't understand it. So what do we need to do? Instead of copy, paste, modify, we need to change our behavior towards link, profile, and reuse. Or maybe the other way around, right? Reuse as much as possible, profile as much as necessary, but make sure you always have the links alive and you have it available in a machine-readable way. Otherwise, you will have no chance to run the same query Manil did, right, this morning against a corpus of data, because you don't know where the data originally came from. You may have a hallucinating model, well, that's one chance, but you may have a model that does exactly the right thing, just on a different data set, and you didn't know about it, right? Because more than one data set was actually available. So the first thing we need to change in our behavior is we need to build these connections. We need to build knowledge graphs for all the data and all the processing or analytics or services as you want to call and name them, right? If you do something like on the left-hand side, you have some attribute name that is rather cryptic, well, nobody can do anything with it. On the right-hand side, it's already much better, right? You do have some URL. It doesn't need to be a URL. There are other mechanisms out there, but it transports the principle, right? You have something others can understand. And others need to understand not only the value here of the daily peak temperature, but they need to understand the unit of measure. They need to understand the sampling regime, right? How was it sampled, and so on. There are quite a number of aspects you need to understand about the data. And what we see very often is that the same research is done over and over in many, many, many places. I give you one example. Recently, we had a meeting in Leipzig, just about 2 hours south of here. And Leipzig has about 65,000 trees in the city. Most of them have been planted after Second World War, so they are about 80 years old. And now they are under severe stress because of the extended dry periods we are now experiencing in summer. So what can you do? You can either water all your trees, well, challenge, or you can replace all your trees with species that are more tolerant to water stress. Expensive, right? But the thing is, the same question appears to almost every city on this planet, right? Humans love green structures. Green structures have an enormous effect on how we experience a city, how we feel within a city. So if we do need to do the same analysis across the world, guess how many research teams are probably actually working on this topic? It's an endless number, right? And whenever we see endless numbers of replications, well, this is a cost element that we can take, that we can exploit, right? That we could minimize the cost by reusing specific elements. But we need to have certain things in place, and one is we need knowledge graphs for all these elements. What we see very often is we see research publications, and if it's a very good publication, it has already links to some data repositories where the data could be found in theory, and it has some links to maybe implementations of the algorithms used in that paper. But if you then follow these links to the data, the first thing you find, what is the number one result that you usually find when you follow a link to the data? The number one is an empty zip file. Because you can easily upload a zip file and the journal will be happy, the editor will be happy, yeah, the data is there, I can see it, but it's almost nothing in there, or it's half empty, right? Or it is not the latest version because at the end you got a little bit under stress and you just uploaded a kind of a, well, slightly outdated version. Same with the processing. But imagine how powerful it would be if the research that is published in that paper would be linked to something that you can directly load into your own processing and your own workflows. Just a thought. So if we do have these elements under control, right, we know what our data actually means, and we have made it available in a machine-readable way, and we know what the dimensions of that value space, right? What values can that data actually have? Well, if both of them are machine readable, we can train our models, and our models can then help us with discovery. They can help us with the provenance trails, right? Whenever you have a product and you can describe how this product was produced, then you are one step further towards reusability and towards integration. But that is exactly the thing, right? Right now, we don't have the information how things have been produced. What you usually need to do if you have some scientific product is you need to read the paper. And then, well, good luck, right? Because you get the paper, you get the result for some specific little area. You want to reuse the same approach because your trees in your city are under similar stress as they are in Leipzig, as they are in Berlin, or in any other city of the planet. But how? Well, first of all, you need to get the real information out of the paper, but then how was it made, right? And you need to have all these question answers. How was it made? What quality is it of? What tools, what algorithms did you use to produce it? What schema is it served? Right? There are many, many, many questions, but we must answer them in order to have AI actually helping us with these two elements of reusability and findability. So there are provenance models, right? These provenance models help us understanding how something was produced. And there are lots of research projects currently out there trying to understand how to ensure elements like reproducibility, like repeatability, right? How can I rerun a process that it produces similar or comparable results? And because that is the baseline to reuse whatever research output I have from one experiment to reuse it somewhere else. There are quality models out there, right? And there are different quality models, so depending on what specific needs you have with respect to the data quality, choose your favorite model. But as long as we select from a limited set of options, right? Limited set of options, like limited set of natural languages, we can live with it because as long as it is limited, we can have transformation engines that translate from one version to the other, from one expression to the other. And that allows tools to learn from it, and it allows tools to help us. Same with the tools, right? Tool description models, schema models. we have all these different models. And there are solutions right now. There are first solutions that exist for these different types of models. They may not be ideal. They may not cover every scenario, every use case. But we can put them and define them as building blocks. So what is a building block, right? What is a building block for a provenance model? The building block is not just a description of a provenance model. It's not a data model for a provenance or something like that. Because what happens if you just describe a model for provenance? Again, nobody reuses it, right? And why don't we reuse it? Well, we want to describe how we produced our results, right? But for sure, we are special. Everyone does it again their own way. So why should I use a provenance model that is already out there? It's not perfectly suited to my needs. How can we now enable people to reuse? Well, the only chance you enable people to reuse something is to make their life much easier. Not easier, right? Because if it's only a little bit easier, people still reinvent everything. You need to make it much easier. So you need to provide them not only the description of your provenance model, for example, but you provide the full tool set, the full tool chain, right? Nobody comes up with the idea, oh, I don't like my browser, I implement my own. Right? If it is hard to do something, if you really see a good benefit in what you get, you reuse. So we need to produce building blocks that consist of everything: the description of the model, testing the model, examples for the model, right? All these elements, the tools that can load the data and extract whatever information you need, tools to write it out, right, to serialize your information. And ideally, you don't even want to bother with it, right? You just want to say, use provenance model X, identified here, and the tool set does all the work for you. And suddenly, your paper is 20 times or 200 times or 2,000 times more valuable because it's not an academic exercise anymore, but it is something that others can discover automatically, right? The key element is really the automated discovery of these elements, because that then allows us to find all these different data sets that are out there, or to reuse specific analytics that others have already built. And we see with these modern platforms that the tendency is towards publication of algorithms. So we have big projects right now in OGC funded by NASA and actually Manil's team and ESA. And the goal is to package your algorithm, ship it to whatever cloud environment you have, and then request an ad hoc deployment and execution with specific parameterization, right? So others can reuse individual analytics built before. So this is the second most important piece, right? After the knowledge graphs that we have now built for all our data and processes, we need to make use of these building blocks, because if you don't use one, no AI tool knows what to expect. You have your product, your data product, but how was it produced? Okay, there's a pointer to some history or some elements that were used as base data for your data to be produced, but as long as it is not machine readable, well, the tool cannot do much with the information you provide. So here's the STI journey, right? This is basically the summary of what I said. To solve the real-world challenges, it is necessary to integrate many Earth observation sources. If you work on a very specific element, okay. But if you want to answer many of the real-world challenges, for example, a simple question like, what should the city of Berlin do to adapt to climate change over the next 50 years? Right? You will not answer this with a single data set from a single environment. So we need to integrate. But right now, all the metadata we have about all these different data sets and processing resources out there is not adequate, right? It does not allow us to discover it automatically. It does not allow us to efficiently integrate it. We can integrate it if we discover it, but it's a rather manual process. But if you know exactly how something was produced, you can use it directly. If you know that the production had some specific constraints, for example, a different sampling regime, well, you know that you may need to do something with the data before you can actually use it, right? So metadata is absolutely key. The machine readability is the next step that we need to bring into place. So right now, the integration is largely a manual process. And when I left university in the late 1990s, the message was always, okay, about 80 to 90% of the time we spent is used for data discovery and preparation. And now, about 25 years later, it's about 80 to 90% of our time is used to data discovery and preparation. It hasn't changed, but we now have the chance with the AI tools that is available, with the techniques that we are now exploring, to modify this very, very manual process that is not scaling well, that requires reinvention over and over, to automate it, right? At least to help us. It will not be magic overnight. You will not run this query I posted at the beginning within the next 2 years. But the hope is that we can execute it in 10 or 15 years. But there's some work to be done before. One element is certainly you need to have some policies and standards in place, right? Interoperability standards simplify some aspect of the integration. They cannot do everything, but as long as you follow a constrained set of options and you describe which one you used, you enable the tools to understand your aspects and then to bring it into new workflows at a much higher level of automatization and efficiency. The power of AI will definitely help us, right? It helps us to navigate the data. Imagine you come across a publication and you just go from this publication to the data that was used. From that data, you figure out, okay, it was used using this sampling regime. Oh, I have similar data in my city, in my country, in my environment, and you can directly reuse it. So the power of AI, well, AI as such, as a tool set, as an environment, can help us to navigate this extremely fastly growing amount of data, not only in size, right? There are so many different data sets coming up every day. And it helps us with the analytics because you don't need to rewrite the same analytics over and over. We need these AI frameworks, right? We need these controlled vocabularies. We need mechanisms to link from one thing to the other. But there are lots of technologies now available that can do this job for us, right? But we need to use them. And when we do this, when we have this AI framework in place, and we have the knowledge graphs in place, well, we are one step more towards explanatory AI. As long as you don't understand all the details about the data that went into some result produced by an AI environment, well, good luck with the explanation of the results produced. But if you understand all these processes, if you understand all these data sets, you are much, much closer. So that is the spatial data handling of the future, right? We need to leverage the power of AI, otherwise we will continue working in environments that do not really satisfy us in many ways. Machine readability is absolutely crucial. As long as we just publish papers and we don't help our LLMs to learn, well, we don't make much progress, right? We still stay at the level where we can maybe get from one paper to another. Yep, I can ask ChatGPT, I have read this paper, find me something similar, and it does a good job already. But we want to get further, right? We don't want to stop with whatever is produced and published in human languages. We want to get to the processes, we want to get to the data to reuse as much as possible. Building blocks are certainly key in such an approach and environment, because look at European data spaces right now, right? Big initiative pushed by several institutions in Europe. Guess how many architectures we have reviewed? 211, right? 211 architectures all promise us they do the ideal job for European data spaces. Yes, because it's always easier, right, to come up with your own architecture than to adapt to something built by someone else. So what do we need to do? Instead of providing these big architectures that are never reused and often disappear once the project that produces them is terminated, we need to decompose it. We need to have a very modular approach. We have to have tiny little blocks that we call building blocks, and you need to be able to select the building blocks you need and bring them together. And yes, there will be competing building block instances for specific aspects. There will not be one provenance model, but maybe 6 provenance models. But as long as it remains a limited set, you can have the transformation engines that allow you, maybe with some information loss, to transform from one to the other. So, and then the last aspect, well, if you have the first 3, then you have helped your environment or your AI environment sufficiently so that it can learn from your data and your processes, and hopefully helps us in future to find the data more efficiently, to integrate the data more efficiently, to solve with the same number of brain cycles and the same number of computing cycles far more challenges that we are facing every day in our society, because there are so many, right? So this is my query. When we meet again in 10 years' time, let me know if you can answer it by then. I think we will definitely be much closer. Will we be able to just run it as such? I don't know, maybe never. But as long as we step a little bit away from the way we do publish elements, and with elements I mean all the elements we produce during a life of a scientist, if we change our behavior slightly, it's not much effort actually, we can get much closer to having an answer to this question. There are a number of research projects right now that we operate in OGC. One, well, at least, one topic is the European data spaces, where we run currently 10 different research projects where these aspects are addressed. We have open science elements where we try to encapsulate specific processing functions and send them to the platform operated by someone else, because we can't repeat everything many times anymore, right? If you want to reprocess your entire Landsat archive, well, good luck, right? But you need to do it from time to time. And we need to reprocess even our full Sentinel archive from time to time. But do we need to do this 12 times? Or is it maybe sufficient to do it 3 times, right? And share the results. What we need to get all this under control, and we need to learn how it actually works. I told you that we do have a number of building blocks already available. That's a great start. But what we need now is an environment that allows us to practice more. But in order to practice more, we need more organizations, more individuals joining in the habit of clearly documenting what they have done, the way they have done it, and such an environment would then be our testbed for further research that hopefully gets us closer to the questions about, well, what's the impact of 20% less parking space and 20% more green spaces in Berlin? And with these words, I thank you very much for your attention.
Yeah, hi, my name is Kai. I'm a PhD student from Professor Demir. Thank you very much for your interesting talk. We have time for a few questions, so if you have any. Okay. Yeah.
Yeah, thank you for the talk. You mentioned data quality, or at least it was on your slides. Do you have a specific definition in mind? What is data quality? Or do you think everybody needs to define it on their own? Or how should we think about what is high quality data?
There is always a starting point. And this starting point could be, for example, an ISO standard like ISO 19156, data quality. It's an ISO standard that allows you to express data quality for data with a focus on geospatial data. That could be an ideal starting point, I think. And then the question is, does it fulfill all your requirements, or are you missing something? And if you're missing something, do not copy, just reference. I use this with that extension. But in many, many cases, we do have these starting points. We are just not using them very often.
I maybe have a question on my own. So what is your recommendation if I am working on a data set? I would like to release the data set. What resources should I use to step in the right direction?
Try to find first the definitions for your data and identify them and make sure your data is linked to these definitions. The problem with these definitions is that for 20 years, and that was unfortunately a situation we were facing, the semantic web promised us something that they never delivered. And everyone was waiting for everyone else to produce all these base ontologies and specific ontologies and definitions that work in this space to do all the magic the semantic web promised. This never happened. But if you are, for example, working in Earth observation and you do, for example, agricultural studies to understand how the crop production develops over the next 20 years, well, FAO provides you a wonderful dictionary for almost every attribute. If you're on the climate space, you have the essential climate variables that are defined. If you are in the remote sensing space, there are the CEOS definition of analysis-ready products that provide you already a great number of starting points, right? Just identify something that is out there and link it. It is not that important which one you use as long as it's permanently available.
Thank you very much. Okay, we have time for maybe one short question, but.
Thanks. Yeah, I really see the compelling case of having these common standards. I think one of the huge problems with adopting them is the cognitive overhead of making sense of these standards, right? I mean, you often need an expert to implement any of these, and OGC standards with XML graphs is really a mouthful for many people. So, yeah, what can we do to lessen the load? You said we need to improve the gain ratio over cost for people to adopt these standards. What can we do?
First, don't use the XML stuff anymore, right? Because that's pretty much deprecated. Use the modern APIs and payloads. And then if you produce one for your data and you have a little engine that reads and writes it, make the engine available. Don't keep it on your local machine. Bring it up to some environment where you can register it as a processing element, publish it, and others will reuse. So yes, a 600-page standard is good for exactly nobody, right? Except you need 600 pages in some cases. But yes, we need to go away from these approaches, and that's why the building blocks are not lots of pages anymore. In the ideal case, it's probably just 3 pages somewhere, well, pages on the web. But it comes with the tools, right? You don't probably produce your own JSON parser, but you use one, right? And what we need to make sure is we bring this reusability because of available tools and components to higher levels. So if you have your generic JSON parser, great. If you have one for your specific data set, wonderful, publish it together with your data because others will then directly reuse it. Otherwise, others will not even use your data because, oh my God, I need to write my own parser for it.